Hi guys, today I'd like to talk to you about nuclear fission. A lot of us are doing nuclear physics next semester, so I thought we'd just get a leg up on that real quick. So, to start with, we can talk about the first ever nuclear reaction that was made in a lab, and we've actually already seen it. If you guys remember Rutherford scattering, he sent alpha particles into atoms to see the effect of scattering of on the alpha particles from the nucleus. But sometimes those alpha particles hit the nucleus, and when they did, those were the first nuclear reactions. So alpha particles hitting nitrogen decomposed into, became a proton and oxygen. So those were the first lab-made nuclear reactions. So to talk about nuclear fission. Nuclear fission is the decomposition of a larger atom into smaller atoms. And so an example of this would be 236 uranium becoming zirconium and tellurium and 3 neutrons. Why does fission occur? It's because the Coulomb force increases and the nuclear force, which is very short range, is diluted because of it. So it becomes unstable. I have a small picture of it here. So 236 uranium becomes unstable. It's the surface area where it's becoming the most unstable and decomposing into smaller particles. And so how do we get to 236 uranium? Well, in the case of a lot of reactors, it's induced. So 235 uranium is hit with a neutron that's traveling with a velocity, so energy, kinetic energy, to become 236 uranium. So the question is, what kind of energy is required of this neutron to hit the 235 uranium to become 236 uranium? The interesting answer is that we already know, and we've actually already found it. It's called the threshold energy by nuclear physicists, and we sort of calculated it in this 350 homework that we did. So I'm just going to go quickly over that. So mass 1 with a velocity, and M2 is stationary. So this is the neutron, this is the uranium. They hit and they join together, becoming the 236 uranium, and have a final velocity. So that's the collision. So this is the equation of energy for that, and this is the equation of momentum, and finding the final velocity with respect to the equation of momentum, we plug this back into the equation of energy, and we can find that Q is equal to negative M2 M1 plus M2. So this is the fraction of the original kinetic energy that is lost. So it's endoergic. It's an endoergic collision. The energy is becoming mass energy. And so, yeah, nuclear physicists call this the threshold energy. So that's the basics of nuclear fission. Now how is this applied? Well, we'll look at that now. This was the first nuclear fission reactor. It was actually in Chicago, underneath, in Chicago University, underneath the football stands, and there was a big controversy about starting it, but it had a lot of safety measures. Yeah. This is a cross-section of an idealized nuclear reactor. So they use fuel cells would be the uranium, and the moderator would be water and graphite. And then the control rods would be cadmium, a substance that can absorb neutrons. And then there'd be a vacuum, and then there'd be a shield, so concrete. The most common setup for nuclear reactors now is this, where water is sent into a reactor pressure vessel. The core, which would be where the fuel cells are and the actual nuclear fission is occurring, heats up the water, and which produces the steam, which turns turbines and then gets condensed again. So yeah. There's been some push for a different kind of nuclear fission reaction in nuclear reactors now, called breeder reactors. So this would mean 238 uranium and which inevitably decays into 239 plutonium. And they prefer that because plutonium would have a much shorter half-life, but there's still a lot of controversy about it. Anyway, thank you so much for watching this. Hope you have a good day.